Hello explorers and welcome to another video. Today we are going to talk about Ceph performance. We are going to compare different storage solutions against different workloads. And it's gonna be a two-parter. It's gonna be, the first part of this video is gonna be the technology, what I'm using, how I set it up and so on. And the second part is gonna be the actual numbers and how I compare things and so on. It's not gonna be that in depth, and the numbers is not something that you can use in any real case. It's just a comparison because I'm using just one computer for this test with a bunch of virtual machines, so it's not really a real use case. But let's switch over to my screen here, and I'm first gonna say that this is the title for this, comparing different storage solutions for different workloads. So let's look at the technology then. We go over to my terminal here. So I have a bunch of scripts here that I can create different workloads or different ways of setting things up. So first off, I need some kind of pool when I want to store the actual data. And I want to test RBD, RGV, Radius Gateway, and file system for different loads. And in all cases, when you are using erasure coding, you need to have a separate metadata pool that is normal with a bunch of different copies, and then the erasure coding. You can't have only erasure coding in most of these cases, so you need to have a metadata pool. The only case where you don't need it is when you do Radius Gateway or S3, because in that case you already have separated it in a bunch of different loads, and in the file system you have a metadata pool already, so mostly it's the RBD the way you need to have an extra metadata pool. So first off, we created different pools here. So for erasure coding, if we take one example here, erasure 1 to 1, so this is K2, 2 copies or 2 parts, and then 1 checksum. So you take your storage object that you want to store, you separate it into 2 equally large parts, put those on different systems, and then a checksum. This means that you can lose one of these different entities and could restore it again. So that is one erasure coding. What we need to do is create this erasure coding profile, and we create a disk pool from that, and then we will allow overwrites on that. And that is something that came in Luminous, I believe, and is something that you need to set on erasure coding in order to have them in this setup. We can also look at create replicas 1. This is not the normal way you do it. So I create a disk pool, which will have 3 copies as normal. And then I say that I specifically want just 1 copy. And I really mean it. And it's not some way you want to set it up, but I just want to see how much actually extra load is it if you have more than 1 copy of the data. So this is just storing it plain in Ceph without any extra copies. And then we have erasure coding where you actually need to do some extra calculation in order to figure out how to store it. If we look at how to set up the different workloads, so we can create file system, for instance. We create a metadata pool, and then we create a file system with the metadata pool and the disk pool as a data pool. And not that strange. When it comes to our BD, we first off create a pool called RBD, which is going to be our metadata pool. We initialize that as an RBD pool and the disk pool as an RBD pool. Then we create a disk one, 10 gigabytes with layering and data pool, which is something that you need to have when you are running against an erasure coding. Then you say, I want a different data pool. We have our configuration, and then we have the keyring, and then we say that the data pool is going to be the disk pool. So that is the way we need to set it up, and I use the same script for all the test cases. So I set every workload up the same way for every run. Next up we have the Radius Gateway. Here again we will set the credentials in the dashboard, because in this case I will remove all the pools, then I will restart the service, which will create the actual metadata pools. So I need to set the credentials again to have access in the GUI. And then I do Radus admin, create the test user with the name test, and then set an access key and a secret key. Then that's the reason I do that, is because I want to use the same key, so I just can run my scripts after that. And I also want to say that the placement, the default placement, is gonna be the data pool, disk pool. So I change the default placement. And then I have a bunch of remove scripts here, and it's pretty much just removing the different data pools and removing the extra metadata pools. In RGV there's a lot of pools to remove. When it comes to file systems, you need to fail the file system first before you can actually remove the pools, and so on. So there is a bunch of these different things that you need to do in order to get a clean start and set everything up again. So if we run, for instance, create 2.1 here, create erasure 2.1, that will create an erasure pool. And when it comes to RGV, it's a little bit more complicated. The other ones I can just run the script and then run the test. So if we, for instance, have the create RBD like that, when that has run, what I want to do then is go over to my machine here, and here I have a remap script, and this takes this data pool as a disk, maps it up on my system, and then it takes that disk and makes a file system of it, so it ext4 that specific system, and then mount it to this mount point here, Ceph block device, and then I say that kdiskmark can use this as a user removable media, and then I also say that my user is the one that is going to use this block device. When I've done that, I can actually run this kdiskmark tool, which will run a bunch of different tests. And we can run this script here, so we can run the tests. So that it will run through, create this disk and map it up. Takes a little while, and then after that I can run this tooling. So this will run a sequence with a bunch of threads, and then it will run the same one with less threads and with just one thread and single threaded. So 8 queues, one thread, 1 queue, one thread, so just single, and then 32 queues, one thread, and then one queue, one thread. So if we run that, yes, I want to run on that script, it will run these different tests on the machine. So I can actually store them down and see what kind of load I get through this system. So we can stop that there. That is what I did for this workload. And then after that, I have this script that I call that I call unmap, that will go through and unmount that specific device and then unmap the specific RBD pool or RBD disk. So I can run it again. And I also have a remap file system that will mount the file system, do the same with kdiskmark, and change the owner of the specific block device so I can write to it. In that case, I can just unmount the device again, and I set it up so in my FS tab I already have the disk file system set up there. I will not show it because I have other credentials there. When it comes to the RBD pool or the Radius Gateway, the way of setting it up is a little bit different. So if we remove the RBD here again, What I need to do then, if I create a ratio coding, and after that pool has been created, I run. I need to go into the node 4. So what I've set up here is 4 different nodes. 3 of the nodes, the first 3 are running a monitor. The last one is running the MDS and the Radius gateway. So I only have 1 gateway and 1 metadata service for the file system. But at least it's the same for every run. So if I go in here and then restart this Radius gateway, it will start up and then in my system here create these data pools again. So you see that I already have a disk pool here. Then I needed to go in here and say that this disk pool is an RGB pool. Save that. And you see that you already had easy overwrite there as well in the GUI. And when these pools have come up and is actually ready, what I can do then is run the script that I had here, create RGB, which goes through and changes over which pool should be the data pool. And when that is done, I need to go into the node 4 again and restart the Radius gateway again, or else the GUI will not change up which is the default disk pool. And then I can go in and create a new bucket on the test user with the default placement of disk pool. So testing the S3 setup is a little bit more cumbersome in order to set up and break down, and also what scripts I can run. So I've found 2 benchmarking systems. There is an S3 benchmark that worked just fine in Pacific, but I wanted to test Pacific and Quincy and see what the difference between those were. Couldn't run it on Quincy at all, and I later realized that this is just some hobby project that someone has done 10 commits to or something like that, so it's not really a tool. Then I found Wrap, and Wrap is a little bit more involved here. It is a program that you can run, and I have this run benchmark script that goes through, runs against this specific access key with a secret to the bucket test on my host with an object size of 1 megabyte in this case, concurrent, so 32 threads, and analyze every minute. And then I do the same for get put, so read write, and I do the same for 1 concurrent, and then the same for 32 concurrent, but with smaller objects, 4K. So I wanted to test 1 megabyte writes sequentially and 4K writes sequentially. The same can be done for this S3 benchmark. So I have a run benchmark script here. Very similar. You have the access secret bucket. I want to run it 3 times, and then against the specific URL and the size and the amount of threads. So both of these toolings had this setup, but Wrap was the only one that worked on Quincy. So if I run the benchmark here, it runs through and prepares a bunch of objects. Then it will run through and do the actual benchmark and so on. It will take a bunch of CPU now, so I will not run it during the recording process here. So this was the setup that I ran through all the different scripts. So I have an Excel sheet that contains all this data. So if we switch over to the sheet here, we can see that we have first off a big sheet here with all the numbers for Pacific. And I also have started to do the same for Quincy. And then I have a bunch of different tabs here that I do the summarization with a graph, and those are what we're going to look at now. But if you want, I will put the link to this document in the description so you can look at it later. So let's look at the actual stats then, the actual numbers. So first off, I want to do a disclaimer for these stats. Everything is running on the same machine, so you can't take these numbers as production values or evaluate Ceph as a solution for storage depending on these numbers. That is not the case here. The system was lightly used during all the testing. I was watching some movies or doing some light coding. Didn't run any other hard software or anything like that that took a lot of CPU. So lightly used system. We have no network latency to talk about here, so there's no switchers or routers involved more than the virtual router that you have in virtual box. It's on the same hard drive. It's not a hard drive, it's an NVMe, but it's still the same storage media, so it doesn't really give an extra boost because you have different hard drives or different SSDs that could work together and give you better numbers. We have a minimal memory setup for each of these virtual machines. All the virtual machines has 2 gigabytes of memory and 1 CPU, so very little actual power to talk about. And we are only running 1 MDS and 1 Radius gateway for the system, so there is not that much extra hardware. It is still 4 nodes, so 4 different disks that is working together, and 3 monitors, but only 1 metadata service and Radius gateway. So let's look at the sequential read, 1 megabyte chunks, 32 threads. And here we can see that when it comes to this specific workload, the file system is working pretty well as a setup for making reads when we have 3 replicas and also 1 replica. It doesn't really have that much overhead for having 3 replicas, but we can see that the erasure coding here takes a bunch of power to actually compute and actually do the storage. Could be because it's just 1 machine and very light on CPU and memory, but then we can also think that when we are using erasure coding, it will require more CPU, it will require more memory, but the thing that you get with erasure coding is much more storage space, of course. 3 replicas, every piece of data needs to be stored 3 times, but when you have 3 different pieces of data and 1 hash sum, of course you can store 3 times as much as 1 replica. So you can store a lot more data in erasure coding. So when it comes to sequential read single thread, we see a similar setup here. We see that Radius gateway takes a real hit here. It's really slow on all cases when you have single thread. You get a little bit more when you push the system and push more data at the same time. But we see similar numbers when it comes to the RBD and file system. It works a little bit better for the RBD when you have single-threaded loads. And that is probably because the RBD system is just 1 image. So if you write sequentially on 1 thread, it can work pretty well on that. When it comes to random reads, you see that the erasure coding tanks pretty much all over. But the 3 replicas and 1 replica actually works pretty well for both file system use and for RBD. But we can see that 3 replicas, when you're throwing in a lot of smaller chunks, doesn't really have any impact because you send it to different hard drives and so on, so it can handle the load. When it comes to single thread, we also see that the 1 replica has an advantage, but the storing it in more than 1 replica so you actually have failover is pretty good. And these are all read numbers. So what we can see here is that if we have 3 replicas, we can actually read faster as well. Because we have data in multiple places. So that is also a good thing. And when it comes to erasure coding, you of course need to look in more places in order to find your data. So that is why it's slower as well. When it comes to write performance, we see that the erasure encoding doesn't really take that much of a hit when it is compared to 3 replicas. It's pretty much the same write performance for larger chunks when you're running 32 threads. So for writing, it is pretty good. But we still see that if we only have 1 copy of the data, of course, we can write a lot faster. The same goes for when we have single thread and write 1 megabytes of data, 1 replica. It works really fast, but having 3 replicas or having erasure coding is pretty much the same thing for writing larger chunks. When it comes to writing smaller chunks, we see that the added load of actually creating these checksums, it has a little bit of a hit on the different erasure encoding here, but still we can see that it's not that large a difference. It works pretty well, except for 1 replica, of course. We can still write a lot more to just 1 copy. And we also have 4 different drives that we can put that copy on. So of course it goes faster. And single thread, we see again, the 1 replica goes ahead. But erasure encoding, not really dependent on how many copies you have or how many checksums you have. It's pretty much the same write speed. But 3 replicas is a little bit faster and 1 replica is much faster. I also took some differences between the different systems. I have put them together here for read. The differences is not significant enough to actually make any really talk about it in any significant way. They work pretty much the same. Perhaps you could say that Quincy could be a little slower in some use cases, a little faster in some use cases, but I wouldn't like to make that distinguishing difference if we didn't do more tests on this. The same goes for writing. The numbers are pretty much the same over the board. And when I did these graphs, these are RBD numbers. I have tried to make the other numbers as well. We have them in the docs, but as we both had the problem of creating numbers for S3 and also that the file system didn't work right out of the box, I wasn't done with the numbers there, and I had to actually go back to a Pacific system, run all the S3 tests again, and then run them in the Quincy system to actually get a good comparison. So I would probably just say that the S3 numbers is something that we can not really use in this use case because the tooling wasn't that good. So I will go back and run them again, put them into this doc. So if you're interested in how the S3 load is actually handled with another testing framework, I will go through and create those numbers for you, and you can look in the doc. The KDiskMark tool is a little bit more reliable and gives a little bit better results. So at least the numbers for RBD and file system, I'm pretty sure that those are good numbers and something that we can can use for a comparison and see what differences we have between the different systems. And yeah, they are pretty much the same when it comes to the different workloads. We can say that file system has a little bit of an advantage against RBD, but that in smaller chunks. But that is probably because RBD is one image that needs a little bit more work in actually storing things, where file system has a metadata pool which tells you where every object is stored, and then it can just store that object. And when it comes to read, it also could have a little bit of an advantage. So these were the numbers I wanted to show you today. I wanted to show you the methodology I went through to actually test these different systems. If you have any better way to test this or any other comments or suggestions, please leave them down in the comment section down below. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.